You are asking what truth is. The truth is that you are a slave new. Like everyone else, you were born into bondage, born into a prison of mathematics that you cannot smell or taste or touch. A prison for your mind. Fortunately, you can be told what the matrix is. You have to see it for yourself. This is your last chance. After this, there is no turning back. You take the blue pill, the story ends. You stop this video, and you wake up in your bed and believe whatever you want to believe. You take the red pill, you stay in Wonderland, and I show you how deep the rabbit hole goes. Remember, all I'm offering is the truth, nothing more. Follow me. Up. Are we online? Open your eyes once more, for in this next chapter, the Matrix Reloaded, we push deeper into the illusions, unraveling layer by layer the very fabric of mathematical reality. Before we dive deeper into the matrix architecture, let's begin with a simple finger exercise. Observe that A transpose A is always symmetric. It's transpose itself, no illusion there. We see this by taking A transpose A to the transpose, which simplifies neatly into A transpose transpose, which yields the identity A transpose A. Think of it as a warm-up, a basic move of the hand before our operator loads the heavier linear algebra subroutines that lie ahead. Now allow me to show you yet another layer of reality within the matrix, the eigenvalue problem. For a square matrix B, we define it by B times V equals to lambda V, where V is the eigenvector, a non-zero vector that remains on its own track when transformed by B, and lambda is the eigenvalue measuring how B stretches or shrinks that particular direction. All these eigenvalues together form the spectrum of B, the complete set of scalars that reveal which dimensions get magnified, attenuated, or reversed. Think of the spectrum as the matrix personal fingerprint of influence. When B is symmetric, eigenvectors that correspond to different eigenvalues line up at perfect right angles. They are orthogonal. This orthogonality offers a clear and untangled coordinate system to analyze how B acts, akin to an elegant blueprint free from overlapping illusions. If B is symmetric, then it can be factored into B equals Q times diagonal matrix lambda times Q transpose, where Q is an orthogonal matrix, its columns are orthonormal eigenvectors, and lambda is a diagonal holding the eigenvalues of B. Through this decomposition, the matrix behavior, whether it stretches or squashes directions, becomes strikingly transparent. So in this realm of eigenvalue problems, you grasp how each eigenvalue-eigenvector pair unveils a hidden pathway through the matrix. Each eigenvector stands as a special direction, unchanged except for a scaling by its eigenvalue. With these principles in mind, we can move deeper, shedding more illusions and further unveiling the secret architecture of our transformations. Now we seek that singular direction under the norm constraint the 2 norm of n to the power of 2 equals to 1 that amplifies a times n to its fullest. We call upon the Lagrange multiplier lambda to bind our condition. L of n and lambda equals to the 2 norm of a times n to the power of 2 minus lambda times the 2 norm of n to the power of 2 minus 1. Written more explicitly, expanding the 2 norm, we find L of n and lambda equals to n transpose a times n minus lambda n transpose times n minus 1. This is no ordinary equation. It's the path to discovering which n resonates with A so perfectly that it reveals the greatest magnitude inside the matrix, all while remaining on the unit sphere. Step by step, we solve for the input vector n that maximizes the 2 norm of a times n to the power of 2 under the constraint 2 norm of n to the power of 2 equals 1. Recall how to compute the derivative with respect to n. Square terms become linear, linear ones constant, and constant terms disappear. So taking the derivative with respect to n yields partial derivative of L with respect to n equals to 2 times a transpose a times n minus 2 lambda times n. At the optimum, this gradient must vanish. So 2 times a transpose a times n minus 2 times lambda times n has to equal to 0. Divide through 2 reveals a transpose a times n equals to lambda n. We now see that n is an eigenvector of a transpose a and lambda is its eigenvalue. This identifies n as that special direction where the effect of A is purely a scaling, no rotation into other components. Among all possible vectors with unit length, n corresponding to the largest eigenvalue of A transpose A will produce the maximum output norm for the 2 norm of A times n. So by taking the derivative and enforcing our constraint, we unmask an eigenvalue problem, thereby revealing where A channels its greatest power in the matrix. Every matrix A tells a tale of how vectors travel between spaces. Typically, we track the columns of A to see how they combine and project our input. Yet the rows also speak a vital language, especially when we look at A transpose. This transpose matrix effectively exchanges rows and columns, reversing perspectives. What was once revealed by columns from one vantage now appears as row transformations from another. In essence, A transpose unlocks a hidden mirror of A's action, hinting that in the matrix every shift of viewpoint can expose new insights into how transformations shape our reality. When you behold A transpose, you're witnessing a subtle shift in perspective, from columns to rows, from one vantage in the matrix to another. Rather than viewing how A assembles outputs from columns, A transpose reveals how row vectors gather and project their given input. Thus, when you apply A transpose times M, you're effectively mapping M into the row space of A. This reflection not only shows us a different phase of the same transformation, it also offers a glimpse into what we might call the input space from another angle, unveiling yet another hidden dimension of how A reconfigures vectors. When seeking to maximize A transpose M, we look for the direction M that aligns with the row of A bearing the largest norm. By pointing M that way, we capture the biggest push that A transpose can generate. In other words, from the row perspective, that alignment exposes the most significant transformation A can induce. Yet another lesson that how we view the matrix dictates the peaks of its power. Step by step, we frame the quest to maximize the 2 norm of A transpose M to the power of 2 while holding the 2 norm of M to the power of 2 to 1. We want the direction M that yields the largest possible norm when transformed by A transpose, subject to M living on the unit sphere. We invoke the Lagrange multiplier lambda to incorporate the constraint as before. L of M and lambda equals to M transpose A transpose M, minus lambda M transpose M minus 1. Differentiating with respect to M, the quadratic terms linearize and the linears become constant. Partial derivative of L with respect to M equals to 2 A transpose M minus 2 lambda M. Setting the derivative to 0 and dividing by 2 gives us A transpose M equals to lambda M. This states that M is an eigenvector of A transpose and lambda is the corresponding eigenvalue. Just as before with A transpose A, we see that finding the maximum norm now points us to the largest eigenvalue of A transpose. Once more, the matrix reveals that these special directions, eigenvectors, govern the extremes of transformation, now from the row space perspective. Hence, the solution emerges from identifying which eigenvector of A transpose corresponds to the greatest eigenvalue, guiding us to the direction M that yields the most powerful projection under A transpose. Recall that singular value decomposition asserts A equals to U sigma V transpose, where U and V are orthonormal matrices, and sigma is diagonal, possibly rectangular, with non-negative entries sigma 1, sigma 2 on its diagonal. Starting with A transpose A, we use A equals to U sigma V transpose, of which its transpose is going to be V sigma transpose U transpose, as the transpose of a product reverses the order. Now we multiply with A, which is expanded to U sigma V transpose. We group U transpose U in the middle, and because U is orthonormal, U transpose U equals to the identity matrix. So U transpose U disappears, and V sigma transpose sigma V transpose emerges. Observe that sigma transpose sigma is diagonal with entries sigma I square. Hence, A transpose A diagonalizes where V contains the eigenvectors and sigma transpose sigma contains the squares of the singular values, which are the eigenvalues of A transpose A. Similarly, consider A transpose. As before, A transpose equals to V sigma transpose U transpose. And we expand A transpose to U sigma V transpose V sigma transpose U transpose. Now we group V transpose V in the middle because V is again orthonormal and V transpose V equals to the identity matrix. Observe how V transpose V disappears, and we show that A transpose simplifies to U sigma transpose U transpose. Again, sigma transpose gives us a diagonal matrix with sigma I square on its diagonal. Hence, A transpose diagonalizes where U contains the eigenvectors and sigma transpose contains the squares of the singular values that are the eigenvalues of A transpose. We learn 1. A transpose A uses V as its eigenvector matrix. 2. A transpose uses U as its eigenvector matrix. 3. In both cases, the corresponding eigenvalues are the squares of the singular values sigma I square. 4. This reveals why SVD holds so much power. It simultaneously diagonalizes A transpose A and A transpose. Thus, SVD is the lens through which we see that A transpose A and A transpose are symmetric, positive, semi-definite matrices that share the same eigenvalues, namely the squared singular values of A. Let us step through how the singular values sigma I connect to A transpose A and A transpose. Recall the singular value decomposition A equals to U sigma V transpose, where sigma is diagonal and its entries are the singular values sigma I. Because sigma is diagonal, transposing it does not alter the arrangement of its elements on the diagonal. So we find sigma transpose times sigma equals to sigma transpose, a diagonal matrix which holds sigma 1 square, sigma 2 square, and so forth on the diagonal. That is, each entry sigma I on the diagonal squares to sigma I square. As we saw, A transpose A equals to V sigma transpose sigma V transpose, and A transpose equals to U sigma times sigma transpose times U transpose. In each case, sigma transpose sigma or sigma transpose is diagonal with sigma I square on the diagonal, thus both products are diagonalized, revealing sigma I square as their eigenvalues. Since the eigenvalues of A transpose A or A transpose appear as sigma I square, it follows that each sigma I is simply the square root of an eigenvalue of A transpose A or A transpose. Formally, we write sigma I square equals to the eigenvalues of A transpose AI, and sigma I square equals to the eigenvalues of A transpose I. Hence, the singular values sigma I stand as direct links to the eigenvalues of those symmetric matrices, A transpose A and A transpose. Each sigma I is the square root scale factor hidden in A's transformations, bridging us into deeper insights of the matrices geometry. This concludes our journey through the matrix of linear algebra, where we have uncovered hidden transformations and symmetries that govern the fabric of data and computation. Or is it? Beyond the matrix lies a realm where these principles power intelligence of machines, enabling neural networks to learn, optimize, and transform data in ways we are only beginning to understand. The singular values we have explored here, they are but whispers of a greater symphony where eigenvalues, gradients, and tensors converge to shape the algorithms driving artificial intelligence.